What if I told you that the latest photographs of 3I Atlas, captured just days ago, contain visual patterns that have left some of the world's most respected astronomers questioning everything they thought they knew about interstellar visitors? What if hidden within those glowing halos and twisting jets lies evidence of something that challenges our most fundamental assumptions about what travels between the stars? This isn't science fiction. This is happening right now, and the clock is ticking toward December 19th, when this mysterious object makes its closest approach to Earth. The images we're seeing today might be the last chance we have to understand what 3I Atlas really is, before it vanishes back into the cosmic darkness, potentially taking its secrets with it forever. Picture this. You're an astronomer staring at your screen late at night, reviewing the latest data from one of the most powerful telescopes ever built. You expect to see a simple comet, maybe some gas jets, the usual signatures of ice sublimating as it approaches the sunday. But instead, what appears on your monitor makes your breath catch. The jets aren't behaving the way they should. The brightness fluctuates in patterns that don't match any comet you've studied in your entire career. The tail structures twist and branch in unexpected ways that challenge standard solar wind models. And then you notice something else, something in the background data that makes you question whether you should even report what you're seeing. Because if you're right, it means we've been looking at this object all wrong from the very beginning. That's the reality facing researchers right now as they analyze the end of November images of 3I Atlas. This isn't about wild conspiracy theories or unfounded speculation. This is about hard visual evidence captured by instruments like the Hubble Space Telescope, by ESA's JUICE spacecraft, by NASA's Distributed Observation Network, and even by amateur astronomers using backyard equipment that complement official observations with unique perspectives. When professional astronomers and dedicated amateurs start comparing notes and finding that the amateur observations are raising additional questions alongside the official releases, something profound is happening in the scientific conversation. You might be wondering why this matters to you. Why should you care about some icy rock tumbling through space, even if it did come from another star system? Because 3I Atlas represents something unprecedented in modern astronomy. We've only confirmed a handful of interstellar objects passing through our solar neighborhood, and each one has rewritten portions of our understanding about what exists beyond our sun's influence. But this one is different. The timing of its closest approach, the intensity of observation it's receiving, the vocal disagreements between scientists about how to interpret its behavior, all of this creates a rare moment when the veil between official narratives and scientific reality becomes thin enough for you to see through. The images that emerged in late November changed the conversation entirely. Before these latest observations, most mainstream sources were content to classify 3I Atlas as an unusual but ultimately natural comet from beyond our solar system. Interesting, yes, but nothing to lose sleep over. Then Hubble delivered its enhanced imagery, revealing a coma structure so complex and dynamic that it sparked immediate debate. The glowing envelope surrounding the nucleus showed asymmetries and brightness variations that don't align neatly with standard cometry models. A primary ion tail and dust tail became visible, with complex structure suggesting varied particle dynamics or compositional variations. And the jets, those streams of material being expelled from the nucleus, displayed a geometry that has some researchers privately admitting they can't fully explain using conventional ice sublimation physics alone. What makes your pulse quicken? What should make you lean closer to your screen right now is that we're living through the discovery phase. The full analysis won't be complete for months or even years. The closest approach on December 19th will generate a flood of new data that could either settle the questions or amplify them beyond anything we're seeing today. But right now, in this moment, we have these November images, and they're telling a story that demands attention. They're showing us an object that refuses to fit comfortably into the boxes we've prepared for it. And here's where it gets personal, where this stops being just another astronomy story and becomes something that might actually shift how you see your place in the universe. Every human being who has ever looked up at the night sky has felt that fundamental question stirring somewhere deep in their consciousness. Are we alone? Are we the only spark of complexity and awareness in an otherwise dead cosmos? Or is the universe teeming with processes, structures, maybe even intentions that we haven't yet recognized? 3I Atlas forces that question out of the abstract and into the concrete realm of actual observation. Those images aren't philosophical thought experiments. They're photons that traveled across space, bounced off an object that originated in another star system, and arrived at our detectors carrying information we're still struggling to decode. Stay with me, because in the next minutes, we're going to go deep into those latest images before the December 19th reveal potentially changes everything. We're going to examine what the major observatories captured, what the spacecraft glimpsed, and why one of the world's most prominent astronomers is publicly challenging the standard interpretation. We're going to look at the specific visual anomalies that are fueling intense debate, explore the speculative theories that have emerged, and understand what's at stake as 3i Atlas makes its closest pass. We're going to separate verified observation from unproven hypothesis, so you can make your own informed judgment about what we might be witnessing. Think about what it means to be alive at this exact moment in history. For thousands of years, humans could only wonder about what lay beyond our world. For hundreds of years, we had telescopes, but no way to distinguish between objects born in our solar system and visitors from interstellar space. For decades, we suspected such visitors must exist, but couldn't confirm them. And now, right now, we're in an era where we can not only detect these travelers but observe them in extraordinary detail. Watching them move through our neighborhood while we capture image after image, building a visual record of something that has journeyed across distances most of us can barely conceptualize. The November images of 3i Atlas are part of that record, and they might represent one of the most significant observational datasets we'll acquire before this visitor leaves our vicinity forever. If you're feeling that electric tingle of curiosity mixed with a hint of unease, that's exactly the right response. Because whether 3i Atlas turns out to be a natural phenomenon with some unusual characteristics, or something that forces us to expand our categories of what's possible, those images are evidence that the universe still has the power to surprise us. They're proof that despite all our technological advancement and accumulated knowledge, we're still capable of encountering something that makes us pause and reconsider. So, here's what I need from you right now, and I don't ask this lightly. If this opening has grabbed your attention, if you're feeling that pull to understand what's really happening with 3i Atlas before December 19th arrives, hit that like button right now. Not just as a casual gesture, but as a signal that you're ready to engage with this material seriously, that you want to be part of the conversation happening around these observations. Drop a comment below and tell me honestly, when you look at images of interstellar objects like 3i Atlas, what truth do you find yourself hoping for, and what truth do you fear discovering? And subscribe to this channel, because what we're about to uncover together is just the beginning of a story that's going to unfold over the coming weeks, and you deserve to have front row access to every development, as the December 19th flyby reveals what those November images were trying to tell us all along. The transition from wondering about the cosmos to actually witnessing its mysteries unfold starts right here, right now, with you making the choice to look closer at what 3i Atlas is showing us. The images that emerged in late November didn't arrive with fanfare or press conferences. They appeared quietly in observation databases, in research team communications, in the feeds of amateur astronomy networks. But within hours of their release, something shifted in the conversation surrounding 3i Atlas. Seasoned astronomers who had been confidently explaining this object as a straightforward interstellar comet began hedging their language, adding qualifiers, noting unexpected features that warranted further investigation. The visual data from Hubble Space Telescope, in particular, delivered the kind of clarity that simultaneously answers questions and generates entirely new ones. When you look at those Hubble images, the first thing that strikes you is the coma, that glowing envelope of gas and dust surrounding the central nucleus. In a typical comet, the coma has a relatively uniform appearance, with brightness that decreases steadily as you move away from the center. But the 3i Atlas coma shows remarkable structure. There are brightness variations across different regions that suggest either uneven outgassing from the nucleus surface or some kind of localized activity that's concentrated in specific areas. The envelope isn't symmetrical. It's distorted, stretched in certain directions, compressed in others, creating a shape that tells a story of forces acting on the expelled material in ways that aren't immediately obvious, from simple solar radiation pressure and solar wind interaction. Then there are the tails. Comets typically display two types of tails: a dust tail that follows the comet's orbital path and curves slightly due to the particles retaining some of the comet's momentum, and an ion tail that points directly away from the sun as charged particles are pushed by the solar wind. The November images of 3i Atlas show tail structures, but they're not behaving quite as textbook examples would predict. One tail component seems to follow the expected ion tail pattern, showing that characteristic straight-line extension away from the sun direction. But there's also a broader, more diffuse structure that doesn't fit neatly into either category. It has characteristics of a dust tail, but with brightness variations and structural features that suggest something more complex than simple particle scattering. What really accelerated the discussion among professional observers was the multi-wavelength analysis. When you examine 3I Atlas in different parts of the electromagnetic spectrum, you're essentially looking at different physical processes. Visible light shows you reflected sunlight from dust particles. Ultraviolet observations reveal excited atoms and molecules in the coma. Infrared imaging can detect thermal emission from the nucleus itself and identify specific molecular species in the outgassing material. The November datasets included observations across this spectrum, and when researchers compared them, they found patterns that didn't quite align with standard cometary composition models. The ratios between different emission signatures suggested either an unusual mix of materials or outgassing processes that weren't occurring uniformly across the nucleus surface. But here's where the story takes an intriguing turn that you need to understand to appreciate why these images matter so much. While the major observatories were releasing their carefully processed and calibrated images, amateur astronomers with sophisticated backyard setups were also tracking 3I Atlas. These aren't casual stargazers with binoculars. These are dedicated individuals with telescope systems that, while not matching Hubble's capabilities, are nonetheless capable of remarkable observations. And what some of these amateurs captured in late November started circulating through astronomy forums and social media, generating intense discussion about features that weren't being emphasized in the official releases. Several amateur observers reported capturing what appeared to be multiple distinct jet features emanating from the nucleus region. Jets are common in comets. They're the visible evidence of material being expelled from specific vents or fissures on the nucleus surface as ice sublimates. But the number, distribution, and behavior of the jets that appeared in some amateur images seemed unusually complex. Instead of a few dominant jets aligned with what you'd expect from a rotating nucleus heated by the sun, these observations suggested activity patterns that were more chaotic, more distributed across the visible surface. Some observers noted that the jets seemed to vary in intensity over relatively short timescales, much faster than the typical rotational period you'd expect from a nucleus of this approximate size. Now, it's crucial to understand that amateur observations, no matter how skilled the observer, don't carry the same evidential weight as data from major observatories. There are calibration questions, atmospheric interference issues, processing choices that can enhance or create features that might not be truly present in the source data. Professional astronomers are right to approach amateur observations with appropriate skepticism, but they're also valuable as independent verification and as sources of high-time resolution monitoring that major facilities, with their carefully scheduled observation programs, can't always provide. When multiple independent amateurs are reporting similar features during the same observation windows, that becomes information worth considering, even if it requires professional follow-up to confirm. The images that dropped in late November essentially created two parallel narratives about 3I Atlas. The official narrative, based on carefully vetted observations from major facilities, acknowledged that this was an unusual interstellar visitor with some features that warranted further study, but nothing that fundamentally challenged our understanding of cometary physics. The unofficial narrative, amplified by amateur observations and by researchers willing to speculate publicly about anomalies in the data, suggested that 3I Atlas was exhibiting behavior strange enough that we should keep our minds open to possibilities beyond the standard cometary model. What you're witnessing here is science in action, not the sanitized version that appears in textbooks after consensus has been reached, but the messy, contentious, exciting process of observers trying to make sense of something that doesn't quite fit their expectations. The November images are artifacts of that process. They're snapshots of an object that's defying easy categorization, captured by instruments designed to answer questions, but instead generating new mysteries. And the timing makes it all more urgent, because December 19th isn't just another arbitrary date. It's when 3I Atlas reaches its closest point to Earth during this passage through our solar system, when our viewing geometry is optimal, when instruments will have their best chance to capture details that might remain hidden at other times. You can feel the tension building in the astronomical community. There are researchers who have staked their reputations on conventional explanations, who see any suggestion of anomalous behavior as irresponsible speculation that might mislead the public. There are others who feel that scientific curiosity demands we take the unusual features seriously, that dismissing anomalies too quickly is how we miss genuine discoveries. And caught in the middle are the images themselves, the actual photographic evidence, waiting for interpretation that might not come until long after 3i Atlas has departed our neighborhood. The late November observations captured something real, something physical, something that traveled from another star system and is now close enough for us to examine in detail. What that something actually is remains the central question driving everything that comes next, including the intensive observation campaign that's ramping up as December 19th approaches, and the promise of even more revealing images that might finally settle the debate or push it into entirely new territory. While ground-based telescopes and Earth-orbiting observatories like Hubble were capturing their stunning views of 3i Atlas, another set of electronic eyes was also turning toward this interstellar visitor, eyes positioned not on Earth, but scattered throughout our solar system itself. Spacecraft designed for entirely different primary missions found themselves with an unexpected opportunity, a chance to observe an object from interstellar space from vantage points that ground-based astronomers could only dream about. And what they glimpsed in those fleeting observations has added another layer of complexity to the unfolding 3i Atlas story, even as the full datasets remain locked behind technical constraints that won't be resolved until well after the December 19th closest approach. ESA's JUICE spacecraft, currently on its long journey toward Jupiter, managed to point its cameras at 3i Atlas during late November. JUICE wasn't designed as an interstellar object observatory. Its mission is focused on studying Jupiter's icy moons, particularly Europa, Ganymede, and Callisto, searching for evidence of subsurface oceans and potential habitable environments. But spacecraft mission planners have learned to be opportunistic. When something interesting passes through a spacecraft's field of view, when there's a chance to capture data that might not be available any other way, they'll often reprogram the observation schedule to take advantage. The JUICE team made that call for 3i Atlas, directing the spacecraft's imaging system toward the coordinates where the interstellar visitor was predicted to be. What JUICE captured was tantalizing but incomplete. The spacecraft's distance from 3i Atlas meant that the object appeared relatively small in the camera's field of view, not the detailed close-up that Hubble could achieve, but still valuable because of the different viewing angle and the different lighting conditions from JUICE's perspective. The initial data transmitted back to Earth showed the coma and what appeared to be jet activity, confirming that 3i Atlas was indeed actively outgassing during this period. But here's where the frustration sets in for researchers eager for more information. The full resolution data, the complete datasets with all the spectroscopic information and multi-wavelength observations, that data is stored on the spacecraft's recorders, waiting for transmission windows when Earth and JUICE have clear line of sight and sufficient bandwidth to handle the download. And those transmission windows are constrained by solar geometry. As 3i Atlas approaches the Sun's position relative to the Earth-JUICE communication line creates interference periods when data transmission isn't possible or is severely limited. This is standard operating procedure for deep space missions. You work around solar conjunction periods when the Sun's massive radio interference makes reliable communication impossible. But it means that the most detailed JUICE observations of 3i Atlas, captured in late November, won't be fully available for analysis until months from now, long after the December 19th closest approach, long after the most critical observation window has passed. NASA spacecraft contributed to the observation campaign as well, though the details of which specific missions captured usable data and what they observed remain somewhat unclear in the publicly available information. Various NASA assets positioned throughout the solar system, from Mars orbiters to outer solar system probes, have communications and imaging capabilities that could theoretically be directed toward an interstellar visitor if the geometry worked out. The distributed nature of NASA's solar system monitoring network means that 3i Atlas could potentially be observed from multiple angles simultaneously, creating a three-dimensional picture of its activity that's impossible to achieve from Earth alone. What has emerged from these spacecraft observations, even in their preliminary and incomplete form, is evidence of variability. The jets that 3i Atlas is producing don't appear to be steady, constant streams of material. They fluctuate in intensity, they appear and fade, they show activity patterns that suggest the nucleus isn't simply rotating with sunlight, triggering sublimation in a predictable way as different surface areas come into view. This kind of variability isn't unprecedented in comets. Many comets show outburst behavior where activity suddenly intensifies for a period before returning to baseline. But the specific patterns observed in 3I Atlas, the timing and distribution of the variations, add to the overall sense that this object is behaving in ways that push the boundaries of what we consider normal cometary activity. You have to imagine what it's like for the mission scientists working with this data. They're trained to be cautious, to avoid overinterpreting preliminary observations, to wait for full data sets before drawing conclusions. But they're also human, curious, excited by the prospect of observing something genuinely unusual. They're looking at these early returns from spacecraft observations, seeing hints of complex behavior, knowing that the full picture is sitting in data recorders millions of kilometers away, inaccessible until the technical constraints of solar system geometry allow the complete transmission. It's like being handed a partially unfolded map of a new territory, enough to know that something interesting is there, but not enough to fully understand what you're looking at. The timing of the data delay creates a peculiar situation. By the time the full spacecraft observations are available for analysis, 3I Atlas will have completed its closest approach to Earth, will have rounded the Sun, will be heading back out toward the outer solar system, and eventually out of our solar neighborhood entirely. The December 19th flyby represents the peak of observational opportunity from Earth's perspective, the moment when the combination of distance, brightness, and viewing angle makes this object as accessible to our instruments as it's ever going to be during this visit. The spacecraft data, when it finally arrives in full, will provide historical context, a record of how 3I Atlas was behaving in the weeks before closest approach. But it won't be real-time information that can guide observation strategies during the critical flyby itself. This creates a strange temporal dynamic in the scientific investigation. Researchers are planning the December 19th observation campaigns based on incomplete information. They're making educated guesses about what instruments to use, what wavelengths to prioritize, what specific phenomena to watch for, all based on preliminary data and early interpretations that might not capture the full reality of what 3I Atlas is doing. It's like preparing for a conversation with someone based on rumors and second-hand descriptions, then hoping you're ready for whoever actually walks through the door. And yet, despite the limitations and delays, the spacecraft observations have already accomplished something important. They've confirmed that 3I Atlas isn't just an Earth-centric phenomenon, that the unusual features seen from ground-based and Earth-orbiting telescopes are real characteristics of the object itself, not artifacts of our particular viewing angle or atmospheric interference. When multiple independent platforms, positioned at different locations in the solar system, all detect similar activity patterns, that's powerful evidence that something genuinely interesting is happening with this interstellar visitor. The probes in the shadows, the spacecraft that weren't designed for this mission but adapted to the opportunity, have added their voices to the chorus of observers, saying that 3I Atlas deserves our closest attention as it makes its way toward that December 19th appointment with Earth's viewing geometry, bringing whatever secrets it holds into the sharpest focus we're likely to achieve. Into this swirling mix of observations, questions, and cautious scientific analysis stepped a figure who has become both celebrated and controversial in astronomical circles. Avi Loeb, the Harvard professor who has built a reputation on asking uncomfortable questions about interstellar objects and whether we're too quick to assume natural explanations for phenomena that might have other origins. In late November, as the images of 3I Atlas were circulating through professional channels and amateur networks, Loeb published a detailed analysis on Medium that sent shockwaves through both the astronomical community and the broader public interested in space mysteries. Loeb's piece wasn't a casual blog post or a speculative ramble. It was a carefully constructed argument drawing on his decades of astrophysics expertise, referencing specific features in the November images, comparing them to theoretical models of both natural and artificial objects, and concluding that the standard cometary explanation for 3I Atlas was, at minimum, incomplete and possibly fundamentally wrong. He didn't claim to have proof of anything extraordinary. What he claimed was that the observations warranted a far more open-minded investigation than the mainstream astronomical community seemed willing to conduct, and that dismissing anomalies too quickly had historically been how science missed important discoveries. The core of Loeb's argument centered on the jet activity patterns visible in both professional and amateur observations. He noted that the distribution and behavior of the jets seemed inconsistent with what you'd expect from a natural comet nucleus responding to solar heating. In a typical comet, jets emerge from areas where ice is actively sublimating, usually concentrated on the side facing the sun or in regions where the insulating dust layer has been breached, exposing fresh, volatile materials. The jets follow predictable patterns tied to the nucleus rotation and the changing solar illumination as the comet moves along its orbit. But the 3I Atlas jets, according to Loeb's analysis of the available imagery, showed characteristics that were harder to explain using this standard model. He pointed specifically to observations showing multiple jets apparently active simultaneously from different regions of the nucleus, with intensities that didn't seem to correlate with what solar heating models would predict. He highlighted the rapid variability that some observers had reported, changes occurring over timescales shorter than the expected rotation period, and he drew attention to what he characterized as unusually structured jet patterns, a structure that seemed less random than you'd expect from uneven ice distribution on an irregularly shaped nucleus. But Loeb went further than just noting anomalies in the jet behavior. He brought up the broader context of interstellar objects and our limited experience with them. We've confirmed only a small number of objects entering our solar system from interstellar space. Each one has challenged our expectations in some way. Oumuamua, the first confirmed interstellar visitor, had an elongated shape and exhibited a non-gravitational acceleration that was difficult to explain using standard cometary outgassing, yet showed no visible coma or tail. Borisov, the second confirmed visitor, looked more like a typical comet, but had compositional characteristics that differed from solar system comets. Now 3I Atlas was presenting its own set of puzzling features. Loeb argued that this pattern, this consistent finding that interstellar objects don't quite fit our categories, should make us question whether our categories are adequate. His most provocative claim, the one that generated both excitement and criticism, was that we should seriously consider the possibility that some interstellar objects might not be natural at all, or might be natural objects that have been modified or instrumented by technological civilizations from other star systems. He floated the idea of a mothership concept, a large interstellar vessel that might seed smaller probes as it passes through star systems, probes designed to study planetary environments or search for signs of life or technology. He was careful to frame this as speculation, as one possibility among several, but he argued that it was no more speculative than some of the contorted natural explanations being proposed to explain the anomalies. The reaction to Loeb's piece was immediate and polarized. Critics within the astronomical community accused him of irresponsible speculation, of misleading the public by giving credence to extraordinary claims without extraordinary evidence, of damaging the reputation of serious astronomy by association with what they saw as fringe ideas. They pointed out that unusual doesn't mean artificial, that natural processes can produce surprising results, that science requires ruling out all conventional explanations before even considering unconventional ones. They argued that the anomalies Loeb highlighted could be explained by factors like irregular nucleus shape, unusual composition, complex rotation states, localized variations in surface properties, and that jumping to artificial explanations was premature at best and pseudoscientific at worst. But Loeb also had defenders, researchers who felt that scientific inquiry requires considering all possibilities, even uncomfortable ones, and that the history of astronomy includes numerous examples of phenomena that initially seemed impossible turning out to be real. They noted that Loeb wasn't claiming 3I Atlas was definitely artificial. He was arguing that we should gather more data with that possibility in mind, that we should design observations that could potentially distinguish between natural and artificial explanations rather than assuming the answer from the outset. They pointed out that the resistance to his ideas seemed motivated more by professional conservatism and fear of controversy than by the actual strength of the conventional explanations. What made Loeb's intervention particularly significant wasn't just the content of his arguments, but his willingness to attach his considerable reputation to publicly challenging the scientific consensus. As a tenured Harvard professor with a long publication record and previous leadership roles in major astronomical institutions, he couldn't be easily dismissed as a crank or an outsider. His credentials forced the community to engage with his arguments, even when they disagreed vehemently. And his public platform, his ability to reach beyond academic circles to the broader public through articles and media appearances, meant that his interpretation of the 3I Atlas observations became part of the public narrative around this object, shaping how millions of people thought about what they were seeing in those November images. Loeb also highlighted something that had been bubbling in amateur astronomy circles, The observation that some of the most intriguing images of 3i Atlas were coming not from billion-dollar space telescopes, but from dedicated amateurs with relatively modest equipment. He questioned why the official releases from major observatories seemed to downplay the very features that were most visible and most puzzling in the amateur observations. Was it simply a matter of different processing choices, different ways of enhancing and presenting the data? Or was there an institutional bias toward presenting results that fit comfortably within established frameworks, avoiding anything that might generate controversy or require uncomfortable explanations? This question touched on a deeper tension in modern astronomy between the traditional gatekeeping role of major institutions and the democratization of observation that powerful amateur equipment has enabled. 50 years ago, meaningful astronomical observation required access to major observatory facilities, creating a natural hierarchy where professional astronomers controlled both the collection and interpretation of data. Today, sophisticated amateurs can capture images that rival professional observations in some contexts, and they can share those images instantly with global audiences through social media and astronomy forums. This creates situations where the public narrative about an object like 3i Atlas can develop partially independently of official institutional positions, forcing professional astronomers to respond to observations and interpretations they might have preferred to address more slowly and cautiously. Loeb's Medium post crystallized this tension. He explicitly praised the amateur observations while questioning the adequacy of official explanations, positioning himself as an advocate for a more open and less hierarchical approach to astronomical investigation. Whether you agreed with his specific interpretations or not, his intervention ensured that the December 19th closest approach would be watched not just by astronomers, but by a global audience aware that legitimate scientific controversy surrounded this object, that the images being captured weren't just pretty pictures, but potential evidence in a debate about the nature of interstellar visitors and our willingness to recognize when something genuinely unusual is passing through our neighborhood. The alarm he sounded wasn't about imminent danger. It was about the danger of missing something extraordinary because we were too committed to ordinary explanations. When you strip away the heated rhetoric and the competing interpretations, when you focus purely on what the images actually show rather than what they might mean, you're left with a set of observed features that are genuinely puzzling, regardless of what ultimate explanation turns out to be correct. Understanding these anomalies in detail is essential, not to jump to conclusions, but to appreciate why 3i Atlas has generated such intense interest and disagreement among people who spend their careers studying objects in space. The November observations captured specific, measurable characteristics that don't perfectly align with the simple models we use to understand cometary behavior. Start with the coma structure, that glowing envelope of gas and dust surrounding the nucleus. In the Hubble images and in high-quality amateur observations, the coma shows distinct asymmetry. One side appears brighter and more extended than the other, creating a lopsided appearance rather than the relatively symmetrical glow you'd expect from uniform outgassing. Now, asymmetric comae aren't unprecedented. They can be caused by jets preferentially active on one side of the nucleus, by the comet's orbital motion carrying material in a specific direction, by solar radiation pressure, affecting dust differently than gas. But the specific pattern visible in 3i Atlas, the degree of asymmetry and its orientation relative to the Sun and the comet's motion vector, doesn't perfectly match any single conventional explanation. Then examine the tail structures more carefully. Professional observations clearly show at least two distinct tail components, which is common enough in bright comets. But the characteristics of these tails raise questions. The ion tail, which should point directly away from the Sun as charged particles are pushed by the solar wind, shows the expected general orientation, but with irregularities and kinks that suggest the solar wind interaction might be more complex than normal. Perhaps the composition of the outgas material is unusual, or the density distribution creates unexpected plasma physics effects. The dust tail component is even more peculiar, showing a brightness distribution and structural features that some analysts find difficult to reconcile with standard dust ejection and solar radiation pressure models. Several observers, both professional and amateur, have reported detecting what appears to be a third, fainter tail-like structure extending in a direction that doesn't fit neatly with either expected tail type. This could be an artifact of image processing, a projection effect from the coma or existing tails, or it could be a real feature, indicating a third population of particles being ejected or influenced differently from the main dust and iron components. Without spectroscopic confirmation of what this apparent third structure consists of, it remains an observational mystery, noted in reports but not yet fully explained. The jet activity presents perhaps the most intriguing anomaly set. Multiple jet features have been documented emanating from the nucleus region. In some observations, particularly those with good temporal resolution showing the object over multiple nights, the jets appear to change. New jets become visible, existing ones fade, brightness levels fluctuate. This kind of variability happens in comets, particularly as new vents open or existing ones become blocked by redeposited material. But the rate and pattern of change in 3I Atlas seems unusually dynamic. Some researchers have noted that the jets don't seem to follow the pattern you'd expect from a simply rotating nucleus with fixed vent locations, where you'd see periodic variations as the vents rotate in and out of sunlight and in and out of Earth's line of sight. Geometric analysis of the jet positions has produced interesting results. When you measure the angles and positions of the jets relative to each other and relative to the nucleus center, some analysts have found patterns that seem less random than expected. There are suggestions of symmetries, of jets that appear to be paired or grouped in ways that are geometrically regular. Now, before you jump to conclusions about what this means, understand that the human brain is extraordinarily good at finding patterns, even in random data. That's part of how our perception evolved. But the patterns being noted in 3I Atlas, jet geometry, have appeared consistently across independent observations and independent analysts, which gives them more credibility than if it were just one person seeing structure in noise. Spectroscopic observations. When you analyze the light from 3I Atlas, broken into its component wavelengths, have revealed the presence of various molecules and atoms in the coma, including water, carbon monoxide, carbon dioxide, cyanogen compounds, and others typical of cometary outgassing. So far, nothing has been detected that's completely alien to comets, but the relative abundances, the ratios between different species, show some variations from what's typical in solar system comets. This could simply reflect the different stellar environment where 3I Atlas originated, different starting materials in its parent star system, different formation conditions. Or it could indicate something about the outgassing processes themselves, about which materials are being preferentially released from the nucleus surface. One particularly interesting observation involves the brightness of 3I Atlas over time. As it approaches the Sun, you'd expect the comet to brighten predictably as more ice sublimates due to increased solar heating. The brightness curve should follow a mathematical relationship related to distance from the Sun and distance from Earth. But 3I Atlas has shown deviations from the predicted brightness curve, periods where it was brighter or dimmer than expected for its distance. These deviations aren't huge, but they're measurable, and they suggest that the activity level isn't simply a function of solar heating, that there might be other factors controlling how much material is being released and when. There's also been discussion about the rotation state of the nucleus. For most comets, you can determine the rotation period by watching how the brightness changes over time, by tracking jet positions as they rotate in and out of view. For 3I Atlas, determining a clear rotation period has been difficult. Different analysis methods have produced different estimates, and some researchers have suggested that the nucleus might be in a complex rotation state, tumbling rather than spinning around a single axis, which would make the brightness and activity patterns much more complicated than for a simple spinner. The thermal properties inferred from infrared observations add another layer of puzzlement. The nucleus appears to have a surface temperature and thermal inertia that don't quite match standard comet models. This could indicate an unusual surface composition, perhaps more rocky and less icy than typical comets, or an unusual surface texture affecting how quickly it heats up and cools down. These thermal anomalies tie into questions about the object's structure and history, about whether it's a pristine sample of interstellar material, or whether it's been modified by some process either in its home system or during its journey through space. When you put all these observations together, you get a picture of an object that's definitely comet-like in many respects, clearly outgassing volatile materials, producing a coma and tails, responding to solar heating. But it's a comet that doesn't quite behave the way our models say it should. Every individual anomaly can potentially be explained by tweaking parameters, by invoking unusual but not impossible characteristics. Irregular shape, complex composition, unusual rotation, heterogeneous surface properties. All of these factors can be invoked to explain specific observations. But the cumulative weight of multiple anomalies, all in a single object, all appearing during the same observation window, creates a situation where the explanations start to feel increasingly ad hoc, increasingly like we're working hard to fit this object into our existing categories, when maybe the object is telling us that those categories aren't quite adequate. This is the essence of the scientific challenge that 3i Atlas presents. Not that any single observation is impossible to explain conventionally, but that the collective set of observations pushes the boundaries of conventional explanation in multiple directions simultaneously. It's at these boundaries where science often makes progress, where objects that don't fit force us to refine our theories, to develop more sophisticated models, to consider factors we'd previously ignored. Whether that progress leads to a better understanding of natural cometary processes in extreme conditions, or whether it leads to recognizing that something else entirely is happening, remains to be determined by ongoing observation and analysis, with December 19th representing the culminating opportunity to gather the data that might finally tip the scales toward one interpretation or another. In the vacuum created by scientific uncertainty, speculation rushes in with tremendous force, filling the gaps between what we know and what we wish we knew, with theories ranging from the plausible to the fantastical. The 3i Atlas observations have generated exactly this kind of speculation storm, amplified by social media dynamics that reward provocative claims, and by the genuine difficulty that even experts have in fully explaining what they're seeing. Understanding this speculation, separating what might have merit from what's clearly unfounded, requires careful thinking about both the science and the psychology of how we respond to mysteries. Avi Loeb's mothership hypothesis has become the most prominent speculative framework, partly because it comes from a credible source, and partly because it's specific enough to visualize, while remaining vague enough to avoid easy disproof. The basic idea is that an advanced technological civilization, wanting to explore other star systems, might not send individual probes directly to each target. Instead, they might send a large carrier vessel, a mothership, on an interstellar trajectory that passes through multiple star systems over time. As the mothership approaches each system, it could release smaller probes designed to investigate that particular environment, gathering data and potentially reporting back. The mothership itself might look like a natural object, either because it's deliberately camouflaged or because it's built from or covered by interstellar material. The probes it releases might exhibit activity patterns, outgassing or maneuvering, that could be mistaken for natural cometary behavior, but that actually serve some investigative function. Applied to 3i Atlas, this framework would interpret the unusual jet activity as potential probe deployment or active maneuvering rather than simple ice sublimation. The geometric patterns some observers claim to see in jet positions would be deliberate rather than coincidental. The rapid variability would reflect controlled activity rather than chaotic natural processes. The composition anomalies might indicate engineered materials rather than unusual ices. It's an interpretation that, if true, would be monumentally significant, potentially the most important discovery in human history. But the critical question is whether there's any actual evidence compelling enough to justify seriously entertaining this interpretation, rather than dismissing it as creative science fiction. The honest answer is that there isn't, at least not yet. Nothing in the current observations of 3i Atlas requires an artificial explanation. Every feature, while unusual, can be accommodated within natural processes, if you're willing to accept that interstellar comets might have characteristics we haven't encountered in solar system comets. The burden of proof for an extraordinary claim like artificial origin is enormous, and that burden hasn't been met. But Loeb's point, which has some validity, even if you disagree with his willingness to speculate publicly, is that science should be designed to detect the unexpected, not just to confirm what we already believe. If you only look for natural explanations, you'll only find natural explanations, even if the reality is something else. Online communities have run with the speculation far beyond what Loeb actually proposed. There are claims that 3i Atlas is an alien spacecraft approaching Earth for first contact. There are theories that it's a weapon system, or a survey platform, or a colonization seed ship. There are assertions that governments know the truth and are covering it up, that the carefully worded scientific statements are designed to prevent public panic. These claims lack evidential support. They're not based on credible analysis of the actual observations. They represent the human tendency to construct dramatic narratives around ambiguous information, to find meaning and intention in random patterns. But dismissing all speculation as worthless would be a mistake, because embedded within the speculation storm are some legitimate scientific questions that deserve serious attention. For instance, there's genuine discussion about whether interstellar objects might carry organic molecules or even microbial life from their home systems, inadvertently or deliberately seeding life across the galaxy. This panspermia hypothesis has been around for decades and has some theoretical support. If 3I Atlas originated in a system with life, if it formed in environments where organic chemistry was active, it might carry molecular signatures or even dormant organisms preserved in ice. The unusual composition hints wouldn't prove this, but they might be consistent with it, warranting careful analysis when and if we ever get sample return missions to interstellar visitors. There's also substantive debate about whether we're allocating enough resources to interstellar object detection and characterization. We've confirmed only a handful of these visitors, but statistical models suggest there should be many more passing through undetected, too faint or too fast for our current survey systems to catch. There's a proposal, which Lobe has championed, for a dedicated interstellar object detection and rapid response system that could identify visitors early in their approach and coordinate intensive observation campaigns or even spacecraft missions to intercept them. The 3I Atlas observations, regardless of what the ultimate explanation proves to be, highlight the scientific value of studying these objects in detail, making the case for enhanced detection capabilities. The speculation about cover-ups and withheld information doesn't have a factual basis, but it points to a real issue around scientific communication and public trust. When official statements seem to downplay observations that amateurs can clearly see, when there's a gap between what professional astronomers are saying publicly and what they're discussing privately in research groups, it creates space for conspiracy theories to flourish. The solution isn't for scientists to speculate irresponsibly about interpretations that aren't supported by evidence, but it is to be more transparent about uncertainty, to acknowledge when something is puzzling without immediately trying to force it into comfortable categories. The image quality controversy that circulated online reflects another aspect of the speculation storm. People have questioned why, with all our technological sophistication, with space telescopes and planetary missions, the images of 3I Atlas aren't crystal clear, why we're seeing fuzzy glows and ambiguous structures rather than sharp photographs that would resolve all questions. This reflects a misunderstanding of astronomical observation. Space is enormous, and most objects are small and distant. Even our best instruments are pushing the limits of what physics allows when observing something comet-sized at interstellar distances. The fuzziness isn't a failure of technology or evidence of image manipulation. It's the reality of observing extremely faint, diffuse objects across vast distances with instruments that, while remarkable, aren't magic. What's interesting about the speculation storm is how it reveals our deep psychological investment in the question of whether we're alone in the universe. The intensity of reaction to 3I Atlas, the eagerness to interpret anomalies as evidence of something extraordinary, the resistance from others who find such speculation threatening to scientific credibility, all of this speaks to how much emotional weight this question carries. It's not just abstract scientific curiosity. For many people, the possibility of confirming that we're not alone would fundamentally change their understanding of humanity's place in existence, would answer questions that philosophers and theologians have debated for millennia. For others, the social and psychological disruption that such a discovery might cause feels dangerous, making them resistant to even considering the possibility seriously. The speculation surrounding 3I Atlas is, in some ways, a dry run for how humanity might respond if we ever do encounter clear evidence of extraterrestrial technology or life. You can see in microcosm the patterns that might play out on a larger scale, the initial ambiguity, the diverging interpretations, the role of individual scientists in shaping public narrative, the tension between institutional caution and public curiosity, the spread of both insightful analysis and baseless conspiracy theories. Whether 3I Atlas turns out to be a completely natural comet or something that forces us to expand our categories, the speculation storm it's generated has value as a case study in how we collectively process the possibility of cosmic significance, how we balance scientific rigor with openness to discovery, how we navigate the space between healthy skepticism and close-minded dismissal of anything that challenges our current understanding of what's possible among the stars. As December 19th draws closer, the astronomical community and the broader public interested in cosmic mysteries are gearing up for what might be the observational event of the year. The date isn't just an arbitrary point on the calendar. It represents the moment when 3i Atlas reaches its closest point to Earth during this passage through our solar system, when the viewing geometry aligns optimally, when the object's brightness and position make it most accessible to the full range of observational tools we have at our disposal. Everything that's happened until now, all the November images and the debates they triggered, has been prologue to this main event. Understanding why December 19th matters requires grasping a bit of celestial mechanics. As 3i Atlas travels on its hyperbolic trajectory through our solar system, its distance from Earth changes continuously. For most of its passage, it's too far away to study in great detail, visible only to the most powerful instruments. But as it sweeps through the inner solar system, there's a window of time when Earth happens to be positioned such that the object passes relatively close to us. Close in astronomical terms meaning millions of kilometers, but near enough that the light we receive is much stronger and the angular size is much larger. This closest approach moment is when we have the best opportunity to capture high-resolution images, to obtain detailed spectra that reveal composition, to track subtle changes in activity over short timescales. The James Webb Space Telescope, humanity's newest and most powerful space-based infrared observatory, has 3i Atlas on its observation schedule for the approach period. Webb's unprecedented sensitivity and resolution in the infrared spectrum should allow it to detect thermal emission from the nucleus directly, to map temperature variations across the surface, to identify specific molecular species in the outgassing material with far greater precision than previous instruments achieved. If there are surface features, if there are localized hotspots where jets originate, if there are compositional variations between different regions of the nucleus, Webb should be able to detect them. The infrared observations are particularly valuable because they penetrate the dust in the coma more effectively than visible light, potentially revealing details about the nucleus itself, rather than just the surrounding cloud of material. Ground-based observatories around the world have cleared their schedules, coordinating observation campaigns that will track 3i Atlas continuously as it passes. This isn't a single institution working alone. It's a global network of professional facilities collaborating to ensure that someone is always watching, that we capture the complete evolution of the object's behavior during the critical period. Different telescopes will focus on different aspects. Some will obtain high-resolution imaging to track coma structure and jet activity. Others will perform spectroscopy to monitor composition changes. Some will do polarimetry to understand the dust properties. Together, these observations will create the most comprehensive dataset ever obtained for an interstellar visitor. But here's what makes the December approach particularly exciting. This is also a prime opportunity for amateur astronomers to contribute meaningfully to the scientific investigation. As 3i Atlas reaches its closest point, it becomes bright enough that serious amateur equipment can capture useful observations. Dedicated individuals with properly equipped telescopes, with the knowledge to process their data carefully, can monitor the object with time resolution that professional facilities, with their competing observation demands, might not achieve. If there are short-term variations in brightness or activity, if jets appear or disappear over the course of hours rather than days, amateur observers watching continuously might detect changes that professional observations, typically scheduled in discrete blocks, could miss. This democratization of observation is profound. 50 years ago, studying an interstellar visitor would have been the exclusive domain of professional astronomers with access to major observatories. Today, a knowledgeable amateur in their backyard can contribute data points that matter, can potentially observe something that changes our understanding. The global amateur astronomy community is energized about December 19th, with forums and social media groups coordinating observation plans, sharing technical tips about optimal settings and processing techniques, preparing to capture and immediately share their images so the world can watch this visitor pass in near real time. The observation campaign isn't just about pretty pictures. Researchers have specific scientific objectives they're trying to achieve. They want to determine the rotation period of the nucleus definitively, which requires tracking brightness variations and jet positions over time. They want to measure the production rates of different volatile species, understanding what's being released and how quickly, which reveals the composition and the outgassing physics. They want to search for fragments, smaller pieces that might have broken off the main nucleus, which would tell us about the object's structural strength. They want to detect any non-gravitational acceleration, the subtle changes in the trajectory that would indicate outgassing is producing thrust, which has implications for the object's mass and activity distribution. There's also a search for precursor molecules, chemical species that might indicate prebiotic chemistry occurring in the coma. While no one seriously expects to detect life itself in a comet, finding complex organic molecules would be scientifically valuable, showing that the building blocks of life chemistry exist in interstellar environments. The spectroscopic observations during closest approach offer the best chance to detect subtle molecular signatures that might be drowned out by brighter emissions when the object is more distant. As the date approaches, you can feel the anticipation building. This isn't just scientists excited about data collection. It's a broader cultural moment when people who rarely think about astronomy are asking questions about 3i Atlas, looking up information, maybe considering whether they can see it themselves. The speculation and controversy have raised the profile of this object beyond the usual astronomy enthusiast circles. The December 19th approach is an event that a significant portion of the world's population is at least dimly aware of, creating one of those rare moments when space science captures broader public imagination. And there's an underlying current of urgency to the whole enterprise, because this opportunity won't last. After closest approach, 3i Atlas will recede rapidly, its brightness fading, its angular size shrinking, the quality of observations declining quickly. Within weeks, it will be back to being a challenging target only for the most powerful instruments. Within months, it will be effectively unobservable, lost in the vast darkness of space, carrying whatever secrets we failed to extract during its brief accessibility. The December 19th window is finite and precious, the culmination of observation campaigns planned over months, potentially the only chance in human history to study this particular interstellar visitor in such detail. So, as the approach unfolds, as telescopes around the world and in space turn their attention to this visitor from beyond our solar system, there's a shared sense among observers that something significant is happening. Whether the final analysis confirms conventional cometary explanations or reveals something that challenges those explanations, whether it settles questions or raises new ones, the December 19th observations of 3i Atlas represent a moment when humanity collectively focused its technological capabilities and its curiosity on understanding an object that originated in an alien star system, traveled for unknown ages through interstellar space, and is now passing close enough for us to study before it vanishes back into the cosmic ocean, leaving us with whatever insights we managed to capture during its fleeting visit. Now comes the moment where you have to step back from the excitement and the speculation, where you have to look at everything we've discussed with clear eyes and honest assessment. What does the evidence actually tell us about 3i Atlas? Not what we hope it tells us, not what would make the best story, but what can we conclude with confidence based on verified observations and sound scientific reasoning? This is where the rubber meets the road, where curiosity has to be tempered with rigor, where we separate what we know from what we imagine. The evidence overwhelmingly supports that 3i Atlas is an interstellar object, something that originated beyond our solar system and is passing through on a hyperbolic trajectory that will eventually carry it back to interstellar space. This much is not in dispute. Its orbital characteristics don't match any pattern that could be explained by an object bound to our sunday. It came from outside, it's here now, it will leave, and it will not return. That fundamental fact alone makes it scientifically precious regardless of any other considerations. The evidence also strongly supports that 3i Atlas is actively outgassing, releasing volatile materials as solar heating causes ices to sublimate from its surface. The coma is real, the tails are real, the spectroscopic signatures of molecules like water and carbon compounds are real. This is behavior we associate with comets, objects composed largely of frozen volatiles mixed with dust and rock. So, at a basic level, calling 3i Atlas an interstellar comet is justified and reasonable. It looks like a comet, it acts like a comet in its broad behavior, it has the composition we expect from comets. But then we encounter the anomalies, the features that don't quite fit standard cometary models, the jet activity patterns that seem unusually complex and variable, the coma asymmetries that are more pronounced than typical, the tail structures that show unexpected characteristics, the brightness variations that don't perfectly match predicted curves, the geometric patterns that some observers claim to detect. These observations are also real, documented by multiple independent sources, not artifacts or imagined features. They demand explanation. The question is whether these anomalies require extraordinary explanations or whether they can be accommodated within our understanding of natural processes. The mainstream scientific position is that they can be explained naturally, that interstellar comets might differ in meaningful ways from solar system comets due to different formation environments and different histories. An interstellar comet formed in another star system might have a different mix of volatiles, a different structure, different surface properties. It might be tumbling rather than spinning smoothly. It might have an irregular shape that creates unusual activity patterns as different surface areas come into view. It might have undergone impacts or thermal processing during its interstellar journey that modified its properties. All of these factors can, individually or in combination, produce the kinds of anomalies we're observing. This explanation has the virtue of invoking only known physical processes, not requiring anything beyond established science. It's the conservative interpretation, the one that respects the principle that extraordinary claims require extraordinary evidence. Given that we've observed relatively few interstellar objects, we shouldn't be surprised if they show characteristics we haven't seen in solar system objects. Unusual doesn't mean impossible, and it certainly doesn't automatically mean artificial. Avi Loeb's position is that while natural explanations are possible, we shouldn't assume they're correct without rigorous testing. He argues for designing observations that could distinguish between natural and artificial origins, for taking the artificial hypothesis seriously enough to actually look for evidence that would support or refute it. His claim is not that 3i Atlas is definitely artificial, but that we don't have enough data to rule out that possibility, and that science should be actively seeking such data rather than dismissing the question as unscientific. There's intellectual merit to this position, even if you're skeptical of its application to 3i Atlas specifically. Science has historically made its biggest leaps when it took seriously possibilities that seemed improbable, when it looked for evidence that could challenge prevailing theories rather than just confirm them. The discovery of pulsars, of black holes, of exoplanets, of dark matter and dark energy, all of these involved taking observations that didn't fit standard models and pursuing them rigorously rather than explaining them away. So the principle that anomalies deserve serious investigation is sound, but there's also a responsibility not to overstate what the evidence shows. The current observations of 3i Atlas don't constitute evidence of artificial origin. They constitute evidence of unusual but not impossible natural behavior. The burden of proof for claiming artificial origin would require finding something that unambiguously could not be natural. Something like clearly manufactured structures, regular signaling patterns, trajectory changes that couldn't be explained by outgassing thrust, materials that don't exist in nature. We haven't found any of that. We've found puzzling features that are ambiguous, that can be interpreted multiple ways depending on your priors and your willingness to speculate. When you weigh the evidence honestly, you have to conclude that 3i Atlas is most likely a natural interstellar comet with some unusual characteristics that we don't fully understand yet. The probability that it's something else, something artificial or modified, is not zero. You can't absolutely rule it out based on current data, but it's low enough that it doesn't warrant being treated as a leading hypothesis. It's worth keeping in mind as a possibility, worth designing some observations that might test it, but not worth the level of attention and speculation it's been receiving in popular discussion. The December 19th observations might change this calculus. If Webb detects something truly anomalous, if the closest approach reveals features that can't be explained conventionally, if we see behaviors that unambiguously point to something beyond natural processes, then the probability assessment would shift dramatically. But until and unless that happens, the scientifically responsible position is cautious interpretation. This is a fascinating interstellar comet that's teaching us about the diversity of objects that exist beyond our solar system, an object that deserves intensive study and careful analysis, but probably not the smoking gun of artificial interstellar technology that some observers are hoping for. This might feel anticlimactic, especially after everything we've discussed about the mysteries and the anomalies and the controversies. But there's profound value in getting comfortable with ambiguity, with acknowledging that some questions remain open, not because of cover-ups or lack of data, but because reality is complex and understanding takes time. The story of 3i Atlas isn't over. The December observations will add significantly to our knowledge. The detailed analysis of data already collected will continue for months or years, potentially revealing insights that aren't apparent in the preliminary interpretations. Future interstellar visitors will be compared to 3i Atlas, building a larger sample that helps us understand which features are typical and which are truly anomalous. Science is a process, not a collection of definitive answers. The value of studying 3i Atlas isn't diminished if it turns out to be entirely natural. We're learning about interstellar environments, about comet formation in other stellar systems, about the population of objects drifting between the stars. Every measurement refines our understanding. Every observation contributes to a bigger picture that's gradually coming into focus. And yes, there's always the remote possibility that future analysis will reveal something extraordinary, that what seems like a natural comet today will turn out to be something else tomorrow. But that possibility has to be held lightly, as motivation for careful study, rather than as justification for premature conclusions that the evidence doesn't support. You've stayed with me through this entire journey, through the images and the anomalies, through the speculation and the scientific debate, through the building anticipation of December 19th. Now it's time to bring it all together and talk about what this means for you, not as an abstract observer of scientific controversy, but as a human being living in a moment when the cosmos is revealing itself in ways that previous generations could only imagine. The story of 3i Atlas is bigger than one interstellar visitor, bigger than debates about jets and composition. It's a story about humanity's relationship with the unknown, about our capacity for curiosity and wonder, about how we respond when the universe hands us something we don't fully understand. Think about the remarkable fact that you're alive at a time when we can observe interstellar objects in detail. For all of human history until very recently, the space between stars was purely theoretical, a vast darkness that we could imagine but never touch. Our ancestors looked at the same stars we see, wondered about what lay beyond, created myths and philosophies, trying to answer questions that had no empirical basis. They lived and died without ever knowing whether anything moved through that interstellar void, whether objects from other star systems ever visited ours, whether the universe beyond our sun's light was empty or filled with travelers we simply couldn't detect. You don't live in that world of ignorance anymore. You live in an era where telescopes can spot something like 3i Atlas when it's still far from the sun, where we can track its approach, analyze its composition, debate its origins, watch it pass through our neighborhood in real time. You have access to images captured by instruments in space, to data collected by spacecraft millions of kilometers away, to analysis performed by researchers around the world. The cosmic mystery hasn't disappeared. We're still full of questions about what we're seeing, but the mystery is now grounded in actual observation rather than pure speculation. That's a profound shift in humanity's relationship with the universe. The November images of 3i Atlas that we've been examining, the upcoming December 19th observations that will be captured while you're reading this or shortly after, these aren't just scientific data points. They're evidence of human achievement, of our species developing the capability to reach beyond our planet and examine visitors from stellar systems we'll never physically visit. Every photon captured in those images traveled across space, bounced off an object from another star's domain, crossed the remaining distance to our detectors, and was transformed into the pictures you've seen. That chain of events, that capture of information from an interstellar traveler, represents the culmination of centuries of technological development and scientific understanding. But it also represents something more personal, more fundamentally human. It represents the persistence of curiosity, even when satisfying that curiosity requires enormous effort and resources. We built the telescopes and spacecraft that observed 3i Atlas not because we needed to for survival, not because there was an immediate practical application, but because we wanted to know. Because humans, uniquely among Earth's creatures as far as we can tell, are driven to understand, to explore, to push against the boundaries of knowledge. That drive is what put instruments in space capable of catching an interstellar visitor's passage. That same drive is what brought you to this video, what kept you watching through this long exploration of images and implications. The December 19th closest approach isn't just an astronomical event, it's an invitation to participate, even from your own location, in observing something extraordinary. If you have access to amateur telescope equipment, if you're part of an astronomy club, if you know someone with the capability to observe 3i Atlas, you have an opportunity to contribute to the ongoing investigation. Your observations, properly documented and shared with the broader community, become part of the collective dataset that future researchers will analyze. You're not just a passive consumer of scientific knowledge, you're a potential participant in its creation. Even if you don't have equipment to observe directly, You're living through a moment when you can follow the unfolding story in near real time. The images being captured during closest approach will be shared publicly, often within hours or days of acquisition. You can watch as the observation campaign proceeds, as new details emerge, as researchers update their analyses based on fresh data. You can engage with the discussion, asking questions, sharing the information with others who might be interested, thinking critically about the different interpretations being offered. This is science as a living process, not a finished product delivered from on high, and you have access to watch it happen. The broader significance of 3I Atlas extends beyond this particular object. Every interstellar visitor we detect and study adds to our understanding of what exists in the galaxy beyond our solar neighborhood. We're building a catalogue of interstellar object types, learning about the diversity of materials and structures that populate the space between stars. This has practical implications for future interstellar exploration, for understanding the environment that any probe we send to another star system will have to navigate. It has theoretical implications for models of planetary system formation and evolution, for understanding how common different types of objects are throughout the galaxy. And yes, there are implications for the search for extraterrestrial intelligence and technology. Even if 3I Atlas turns out to be entirely natural, the techniques we're developing to study it, the methods for detecting and characterizing interstellar visitors, these same capabilities would allow us to recognize an artificial object if one ever did pass through our solar system. The infrastructure we're building to observe objects like 3I Atlas is dual-use infrastructure that serves both natural science and the search for technosignatures. Every improvement in our detection sensitivity, every advancement in our analysis methods, increases the probability that we would recognize something extraordinary if it appeared. But I want to bring you back to something more immediate, more emotionally resonant than long-term implications for science and exploration. I want you to think about what it feels like to know that 3I Atlas is out there right now, perhaps visible in your night sky if you know where to look, a visitor from another star system passing close enough for us to study. Think about the journey that object made, the unimaginable timescales and distances involved, the stellar environments it might have witnessed during its travels. Think about the fact that it's carrying information, in its composition and structure and behavior, information about places and processes completely foreign to anything that originated in our solar system. That visitor doesn't care that we're watching. It's not here for us. It's not trying to communicate or make contact. It's simply moving through space on a trajectory determined by gravitational interactions we can only partially reconstruct. But its passage gives us a glimpse, however incomplete, of the broader universe that exists beyond our sun's influence. That glimpse is precious, precisely because it's rare and fleeting. 3I Atlas will pass, will recede back into the darkness, will continue its journey to wherever gravity eventually carries it. We have this moment, these weeks of closest approach, to learn what we can. After that, we wait for the next visitor, whenever that might come, and hope that our instruments and our understanding have improved enough to learn even more. There's a melancholy in that temporal limitation, in knowing that this opportunity is finite. But there's also beauty in it, the same kind of beauty that exists in any transient phenomenon. The cherry blossoms that bloom briefly and fall, the meteor shower that lights the sky for one night, the solar eclipse that traces its path across a landscape and then passes. These temporary events carry an intensity of experience precisely because we know they won't last. The December 19th observations of 3I Atlas have that quality. This is the moment. This is when we have our best chance to understand this visitor, and that urgency adds weight to every observation, every analysis, every discussion about what we're seeing. So, here's what I'm asking from you as we close. If this exploration of 3I Atlas has captured your imagination, if you've felt that stirring of cosmic curiosity that's fundamental to human nature, take action on that feeling. Hit the like button not just as a mechanical gesture, but as an acknowledgement that this matters, that questions about interstellar visitors and what they reveal about the universe deserve attention and engagement. Drop a comment below sharing your honest reaction to what you've learned. What aspect of the 3I Atlas story resonates most with you? Are you more drawn to the scientific puzzle, the technological achievement of observing it, or the philosophical implications of interstellar visitors passing through our system? What would you most want to know if we could somehow interrogate this object directly and get definitive answers? Subscribe to this channel because the December 19th observations are going to generate follow-up content as the data gets analyzed and interpreted. You'll want to know what Webb detected, what the ground-based campaign revealed, whether the closest approach answered the questions or generated new ones. This story is unfolding in real time, and staying connected means you won't miss the next chapter. Share this video with anyone in your life who cares about space, about cosmic mysteries, about humanity's relationship with the unknown. These are conversations worth having beyond the isolation of individual viewing, worth discussing with friends and family, worth bringing into broader awareness. But more than anything else, I want you to look up, not just metaphorically, though that too, but actually go outside on a clear night soon, find a dark spot away from city lights if you can, and spend time looking at the stars. Know that among those points of light are other star systems, some of which might have sent objects like 3i Atlas on journeys across the galaxy. Know that the space between those stars isn't empty, but populated with travelers, most of them too small and dark for us to detect, occasionally one passing close enough and bright enough for us to notice. Know that you're part of a species that has developed the ability to recognize and study these visitors, that has built the tools to transform photons into knowledge, that cares enough about understanding to invest enormous resources into satisfying curiosity about objects that have no immediate practical impact on our daily lives. That act of looking up, of connecting yourself to the broader cosmos, of acknowledging that you're a small part of something incomprehensibly vast, that's what the 3i Atlas story is ultimately about. Not whether this particular object is natural or artificial, though that's an interesting question. Not whether the jets are behaving exactly as cometary models predict, though that's scientifically important, but whether we, as a species and as individuals, maintain the capacity for wonder when confronted with the unknown. Whether we let mysteries energize our curiosity or paralyze us with fear and uncertainty. Whether we approach the cosmos with humility about how much we don't know, balanced with confidence that we can learn, that every question we answer illuminates the path to asking better questions. The images of 3i Atlas, captured in late November, the observations being gathered during the December closest approach, these will be analyzed and debated for years to come. Papers will be published, models will be refined, our understanding will gradually sharpen. Maybe future observations will reveal that everything was exactly as straightforward as the conservative explanations suggested. Maybe there will be surprises that force us to rethink aspects of cometary science or interstellar object characteristics. Maybe, just maybe, though this seems unlikely based on current evidence, there will be a discovery that changes everything we thought we knew about what moves through the space between stars. But regardless of which way the analysis ultimately goes, regardless of whether December 19th delivers clarity or more mystery, you'll know that you were aware during the unfolding, that you paid attention when humanity encountered a visitor from beyond and tried to understand what it was telling us. That awareness, that engagement with discovery as it happens, rather than learning about it as historical fact years later, that's a gift of living in this particular era of human capability. Previous generations couldn't have this experience because the technology didn't exist. Future generations will have it as routine, as normalized, losing perhaps some of the excitement that comes from witnessing these early observations of interstellar visitors. You're in the sweet spot, living through the transition from blindness to sight regarding interstellar objects, able to appreciate both how far we've come and how much further we have to go. The November images of 3i Atlas, those frames we've examined so closely, they're evidence of that transition. They show us something from beyond our solar system, with a clarity that would have been impossible just decades ago. Yet they still leave enormous questions unanswered, questions that future capabilities will eventually address. You're witnessing the process, seeing how knowledge grows through observation and analysis and debate, how science doesn't deliver instant answers but gradually builds understanding through careful work. So stay curious, stay engaged, watch as the December 19th data gets released and analyzed. Follow the ongoing discussion about what 3i Atlas reveals and what it conceals. Keep asking questions about what else might be out there, what other visitors might pass through our solar system in your lifetime, what we might learn as our detection and observation capabilities continue to improve, and most importantly, maintain that sense of connection to the cosmos, that awareness that you're not separate from the universe looking in, but part of the universe becoming aware of itself, a configuration of matter and energy that can observe and understand other configurations across vast distances and timescales. The call to the stars isn't about expecting them to answer with voices or signals. It's about us choosing to reach toward them with our instruments and our intelligence. choosing to care about understanding, even when that understanding is difficult and incomplete. 3i Atlas is a small part of that larger human project, one interstellar visitor among many that will eventually be detected and studied. But it's here now, it's observable now, it's raising questions now. And you have the opportunity to be part of the conversation, to engage with the mystery, to experience firsthand what it means when humanity encounters something from beyond and asks what truth it carries, what story it tells about the vast and ancient cosmos through which we all travel together on our small blue world. Watching visitors pass and wondering what they might reveal about realities we're only beginning to glimpse,